My name is Barry Burr. Been working at Bryan Research for about 15 years, and my role is to develop business in the refining industry. And I don't have very much experience with sulfuric acid, and until January, I'd never thought about simulating it, and I couldn't tell you the basic reactions that proceed to sulfuric acid production. But I've done a little work on it this spring, and I've done a lot of ProMax modeling work. So compared to many other models that I've built, I'm pretty impressed at the quality and the accuracy of ProMax in matching the plant data for sulfuric acid production. So I feel I can give a webinar on simulation of sulfuric acid production. I'm not much use at telling the public about the technology itself, and there's a lot of aspects of it I don't know about. But as far as the simulating of it, I think I know the key, the main points of simulating and sulfuric acid production that would apply to almost any of the process technologies out there. So what I want to do is I want to go through two different simulations of sulfuric acid plants. The first one will be a spent sulfuric acid regeneration plant. So it's taking spent sulfuric acid from a refinery alkylation unit at about 90% sulfuric acid, and it's kind of weird. You go from 90% sulfuric acid and you break it all the way down to SO2, and you build it back up through SO3 and back to sulfuric acid again. There's no regeneration just to remove the impurities. You take it back to its basics and build it back up. And so I'll go through that process. And there's another process that I've simulated, which is a wet sulfuric acid process. So I'm going to go through the simulation of that. And afterwards, I have this demonstration section. So I'll demonstrate the key things that I think are unique or particular to sulfuric acid production. And these are the combustion section, where you burn your sulfurous feedstocks, and then the catalytic converter sections, where you react SO2 with oxygen to create SO3, and then the absorbers, where you contact sulfuric acid with water, or SO3 with water, to form sulfuric acid. Three things about sulfuric acid production plant simulations that I think separate them from other typical simulations that you might perform. So basically, with sulfuric acid production, you have a feedstock that contains some sulfur, and you oxidize it. Or actually, in the case of sulfuric acid, you decompose it at high temperature. You oxidize it, and you oxidize your sulfurous feeds to SO2. So in this case, our main sulfurous feedstock is spent sulfuric acid. And if we double click on this stream, we can see that this sulfuric acid feedstock has here 89.7% sulfuric acid. And it's just at ambient conditions, liquid phase. And we feed that along with air to provide the combustion oxygen, and we're going to provide the combustion oxygen to an amount that gives us 3% oxygen at the outlet. So we're going to combust completely all the sulfur. There's also some H2S feed. This provides extra heat. This has a lot higher heating value, and also if you need to make up sulfur because you don't have enough sulfur for your needs in your spent acid, you can have that. And then we're also going to add some natural gas for temperature control. So in this case, we have a a burner. We have two different burners. They're both simulated the same way. And we double click on the burner. We go to the process data tab, and we're using Gibbs minimization. So there's no reactions to define. You just choose which components are going to participate in the Gibbs minimization. And in this case, we're going to let all the components present are going to participate in this Gibbs minimization reaction. And you see the inlet does not have any SO2 or SO3, or it has a lot of sulfuric acid and H2S. And then on the outlet, after both burners have done their thing, you're going to see that we have no longer any H2S. We have 3 mole% oxygen, and the sulfuric acid is basically gone. And so now we have an SO2 rich stream at a very high temperature. And there's an equilibrium that exists between SO2 and SO3. So as the temperature goes lower, you're going to find that more SO3 exists in your burner outlet stream. So, you know, probably in this process here, you'd like to have a higher temperature and less SO3, because that ends up kind of being a waste. It doesn't make it to the sulfuric acid product. But we have an airflow rate has a solver on it. So we're adjusting the airflow rate so that we get 3% oxygen at the burner outlet. And we also have a natural gas flow rate solver. And its objective is to make sure that we have 1911 degrees at the outlet of the first burner. So that's two salt. We also have another solver that is adjusting the spent acid distribution so that some of it goes to the first burner and then some goes to the second. So we have a solver that's making sure that the temperature past the second burner equals 1735 degrees. So that's how we're simulating this combustion section of this particular process. And for the wet sulfuric acid, it's basically the same, except that the sulfurous feedstock is going to be different. Now, in the spent sulfuric acid regeneration process, it's a pretty old process that requires a dry or water-free gas before it enters the catalytic converters. So we have two flow sheets here. One thing I forgot to mention is that in the combustion flow sheet, there is the environment that we're using is just Ping Robinson. So if you're used to using ProMax, you know that for every flow sheet, you need to choose an environment. And here we've built an environment that uses Ping Robinson as the liquid and vapor phase property calculation algorithm. And then we have the components needed to carry out this reaction and all the other subsequent processing. I think we're going to use the same component list throughout the entire simulation. And now as we move on to this quench section, we have our objective is to take the effluent from the burners and cool them down using a water quench system. And the environment we're using here, can't remember for sure. Let's see. I think it's going to be the liquid acid environment, but I'm not sure. Yeah, here, because there's potential for acid to be in the liquid phase, you see this circulating loop. It ends up having 8% sulfuric acid because this is occurring. we switched to a different thermodynamics package that is currently something that is a custom package. Its basic package is NRTL, Ping Robinson, or SRK. So we select NRTL as the basic package, but then we choose this use custom option, and there are changes we have to make to the molar enthalpy and the molar volume properties. So if we go here to molar enthalpy, it'll populate, and instead of the normal selection, we go down here to the very bottom to this special selection for the light liquid and heavy liquid mixture properties. It's called the BRE ProMax Electrolytic Heat Capacity Laliberte class. So this is a new option that we've added in ProMax 5.0, and it now allows us to simulate these acidic liquid at pretty high strengths, these acids and bases at pretty high strengths in the liquid phase. We're able to simulate those, whereas we really couldn't do this before ProMax 5.0. So this is a new capability we've added, and it lets us simulate this. And I'm trying to get this kind of complicated environment configuration improved, so it's one of the predefined packages that is much easier for use. But in the meantime, we have to go through this step to make these changes to invoke this Laliberte class, and that lets us simulate the phase equilibrium for stronger acid and bases in the liquid phases. And it's not an electrolytic model, it's a pure component model. There's no ionization that's occurring. So if you're used to how we treat amine solutions, that would be an ionic package, and you would see a breakdown of species based on their ions, but you won't see that here with an NRTL-based thermodynamics package. But so you see here we have the inlet gas coming in at 577 degrees, and we're cooling it so that it exits at 125 degrees. But it's still a wet gas. It's got, at this point, it's got water concentration. Got 6.8% water in it. And we need to remove the water before we can proceed to the catalytic conversion beds. And so we have a drying process. First, we need to add some extra air, because we're going to need air later on for the time when we react SO2 with oxygen to create SO3. So we're going to add some air, and we have a solver on here to make sure that we attain this oxygen to SO2 ratio of 1.2 molar ratio. So we're going to add enough air there, and then we're going to dehydrate the SO2 gas. And it's kind of interesting how this is done. The way that you dry it is you use a really good dehydration agent, which is strong sulfuric acid. So in this plant, there's large tanks of 93% sulfuric acid in storage, and that sulfuric acid is passed down this tower, and it contacts the SO2 gas, the wet SO2 gas. It absorbs the water, and it loses a little bit of strength, but it takes the water away from the SO2 gas. So now it's a dry. You see it went from 6.8% down to 0.15 mole percent water. So now it's a dry SO2 gas. We're going to proceed to the catalytic conversion units. So here we have 4 beds of catalyst, and we take the dry SO2 gas and we preheat it. All these reactions are exothermic. They need to be cooled, while at the same time we need to preheat our incoming gas. So this has to thermally balance, and we preheat the gas up to 850 degrees, and we go into these catalytic reactors. Each of these are simulated in the same manner. We have a, in this case, I didn't really understand enough, and I created a reaction and set it to be an equilibrium reaction type. And that's how these reactors are working. But you could also run these using Gibbs minimization, and I'll show how that is done in the next simulation and in the demonstration project. So here we have a reaction we've defined where SO2 plus oxygen goes to SO3, and it is conducted. Here you can see the SO3 to SO2 reaction, SO3 to SO2 reaction. You can see the species, the stoichiometry set. It's an equilibrium reaction, and we are choosing the K equilibrium to be calculated by Gibbs minimization. So it's really the same thing as doing Gibbs minimization with only these three compounds selected. And that's what we'll do later on because it's easier. But all the beds are set up this way. There's also an approach to equilibrium, or in the process data tab for this reactor, you can see that I've set this thing called a bypass fraction. So the reactions do not go to equilibrium. They approach equilibrium. Well, at least on this, to match this one, I was able to match it best by having a slight bypass on this one and then no bypass on the others. I think technically there's supposed to be some small approach to equilibrium on all of these, but I was able to best match the plant data with these bypass fractions. And what the bypass fraction means is that it pretends that 5% of the inlet is just bypassed around the reactor and then remixed with the outlet. That's what a bypass fraction does for you. So it simulates, this would be almost like saying you have 95% conversion. And then also to provide a good match, I had to remove a little bit of energy, which I think is probably happens due to just heat losses to the ambient. I had to remove a little bit of energy. I don't normally do this, and I probably wouldn't do this if I was just designing a system, but if I was trying to match to some plant data, I will pull out a little bit of energy if it seems reasonable, and it gives a little bit better match to do that. So that's the process I went through to simulate the catalytic beds. All the other beds are treated the same way. So now we have a gas that doesn't have very much SO2 anymore, but now has a lot of SO3. So the catalyst has converted our SO2 rich gas into a SO3 rich gas. But there's still no sulfuric acid yet. So we're going to do a demonstration exercise later on to simulate how to configure reactors in the catalytic beds for both the wet and the dry process, this being the dry process here. And then we move over to the absorber, and once again we have an SO3 rich gas, and we don't just mix it with water to form sulfuric acid. I mean, that's the reaction that occurs. But if you just mixed SO3 rich gas and water, there's a lot of heat of reaction that has to be absorbed by the contents. So to provide a really good heat sink, we start with a rich sulfuric acid stream. So we're taking 98% sulfuric acid, and we're reacting it with, and it contains the water necessary for the reaction. So the 2% water in this 98% acid stream is the reactant that reacts with the SO3 to form SO2. And this is, in ProMax, we've had reactive distillation columns for several years, but I had never had the need to use one until I encountered this absorber. So we're still in the NRTL package where we can handle the strong acids and bases. But in this column, we're fractionating while at the same time reacting. So in the process data tab for this column, we have our normal column specifications and things about stages, mainly the pressure profile. But here we have this item that I've never used before getting into sulfuric acid simulations. This user reactions tab is a new one for me, and it requires that you define a reaction. So here I've had to define a reaction set I call SO3 absorption, and I choose this. You choose this reaction set, and then you check which stages you would like the reaction to occur on, and then you can set a conversion constant. So here I've decided that the reaction is going to be conversion reaction, and I'm saying that on each stage in the light liquid phase, the conversion factor is going to be 0.93 because that provided a good match to the plant data. So here is, it's kind of an odd thing to see as a reactive distillation column. At least it's very rare in my experience to encounter these. And then, so now we've converted the SO3 into sulfuric acid. If you look at the vent, there is very little SO3 remaining. There's some SO2 remaining, and that's important because it's a pollutant, and we have to take that down to regulatory standards. But here we have absorbed the SO3 into the 98% acid, and now the bottoms is richer in sulfuric acid. It's now 98.6%. And it's also got a higher flow rate. So instead of 14,520 gallons per hour, now we have 14,885. So that difference plus the extra strength, that's where your new sulfuric acid that you've produced throughout this process is appearing. It's appearing in this extra flow rate and extra strength. Now, in this case, there's a system of tanks. I don't want to get into this, but this is all meant to control the, you add a certain amount of water to bring your acid strength back to 98%. So you're maintaining two tanks at different acid strengths. And this is just the controls for doing that. But I really don't want to get into that in this discussion. And now that vent gas that has some SO2 in it, it has to be scrubbed of the SO2. And in this case, there's a caustic, a two-stage caustic scrubbing system that removes the H2SO4. This system is, now we're getting into where we need a electrolytic environment. So we're now using our caustic treating Ping Robinson environment because this is a much more appropriate. We don't have a strong acid phase, but we have this caustic that we're very experienced with working with, and we use that to absorb the SO2 out of the off gas. And you see here our SO2 is down from about 0.1 3,000 ppm down to 20 ppm with this process. So that is a quick rundown on how to simulate a spent acid regeneration system. Kind of an old technology. It's got a scrubber for SO2 removal. There are some newer designs that will use an extra intermediate absorber, but this is one way of skinning the cat. And I think in sulfuric acid, there's many ways to skin the cat. So at this point, are there any short questions that I can answer? I'll try to answer.
There's There's a
Yes.
question by Joe in the chat that says, why to use two burners to model combustion chamber versus one single block, I guess.
I think it would work fine to use a single burner, and I think you would get the same answer if you used a single burner and the final outlet temperature of the second burner as your target. I think you would get the same answer. It's just because this particular plant had two burners and two different temperatures to target, but in general, I would probably use one burner and one outlet temperature. I think in real life, there might be some, there might be some advantages to having two burners because of the equilibrium of SO3 and SO2. Maybe those are kinetic reactions to some extent, and we're not capturing any of that kinetics in our model. We're just assuming they reach equilibrium, which is a pretty good assumption, but there might be slight differences you see with two separate burners because of the kinetics of the SO2 or the sulfur oxidation. That's my only guess. I don't know. Does anybody else know the answer to that? It's a good question, but I just don't know enough about sulfuric acid processing to know the answer. And I expect there's several people here that know a lot more about the topic than I do. All right. Okay, so there's no more questions about the spent sulfuric acid process. Let's move on to the wet sulfuric acid process. Let's see. Okay, here's the wet sulfuric acid process. Okay. Just like in the spent sulfuric acid, here we just have one burner. They may have two. They may really have two different burners, but we're simulating it as one burner right here. So we're taking air and we're providing enough air to let's see, actually we're just setting the airflow to match the plant's airflow. In this case, we're not trying to reach a target. They're probably trying to reach a target oxygen content in the outlet, but I just saw the measured flow rate and use that. We have H2S feed. It's only about for H2. It's only about 20% H2S. So this would not be. We do a lot of Klaus sulfur recovery units, and it's a very common thing for brine research and engineering and ProMax to do. But this would not be a good feedstock. It's got not nearly enough H2S in it to be a good feedstock to a Klaus plant. So it's I guess they decided that they're going to take this H2S acid gas that they're generating. It's a lower strength and going to make sulfuric acid out of it. So we burn it. Same kind of Gibbs minimization with general, and all the components are set. We have no bypass fraction set. We do have. It never hurts to put 2 as the maximum phases, even though it's very unlikely that's going to happen here. But as you're starting out the simulation, you might have some low temperatures and things that before you get the simulation working properly, you might run into that situation and your reactor will solve through it. But up at these conditions, I could set that back to 1 maximum phase and it would be okay. And here is our SO2 rich gas. And we now go to the catalytic system for this SO2 rich gas. This is SO2 rich and it has water. It is, let's see, SO2 is 4%, water is 10%. So this catalyst doesn't require a water-free or an anhydrous feedstock. This catalyst can perform both the SO2 oxidation to SO3, and it can also simultaneously perform the SO3 hydrolysis to sulfuric acid. So in this reactor, it's going to be simpler than the one I had before because we use Gibbs minimization, but we select the components for those two reactions. We select SO2 and oxygen, which form SO3, and we have SO3 selected along with water that it reacts with to hydrolyze to sulfuric acid. So we have those components selected. So the equilibrium amount of those is reached in each of these beds. And we have 2%, 5% bypass on these beds to best match the data. And then a small amount of heat is being extracted also. And I think that can be well explained just by ambient heat losses. And you see the expected compositions out of each of these. We cool it. Also, this is a reactor, but it's not a catalytic reactor. It's only considering the components for the SO3 hydrolysis. So it's only considering the SO3, the H2SO4, and the water. But you see SO2 and oxygen are not selected. So as we're cooling the bed 3 outlet gas down, we are only creating sulfuric acid, but we're not converting any more SO2 to SO3. At this point, we have very little SO2 remaining. So most of that has been reacted. We have some SO3 remaining. Not all of it has been converted to sulfuric acid, but we have mainly the components that we're interested in. We have some SO3 and some sulfuric acid. And those proceed to the condensing section and the quench. So in the converter section, we were using Ping Robinson again, just as we were with the combustion section. But now that we're in the condenser section, we're switching to that NRTL with the Laliberte enhancements for molar enthalpy and molar volume. And here we have a condenser column where the gases rise through. There's a condenser, reflux condenser basically, that's creating reflux, which falls back down. And this column has the same SO3 absorption reaction occurring in it. So this is a reactive distillation column. So the SO3 absorption is occurring in here simultaneously with distillation, and that produces a acid-rich stream, and we have to add some water to it. We have to add some water so that we can bring the acid strength back down to 93%. So we're producing 93% acid with this condenser. And then the vent gases go to a quench column to cool down. And the excess water that is accumulated in here is sent back down. Actually, we add some water and we also send some water back. And it's a pretty strong acid system here. You see it's whatever's circulating in this quench circulation loop is 32% sulfuric acid. Some of that is returned here to also help produce acid product. The quench has sulfuric acid being formed, and so we also have the SO3 absorption reaction checked on in this quench column. And now we have the gases that are going to the scrubber. We still have too much SO2 in here, so we have to do some SO2 removal. We have some SO2, and 170 ppm SO2 and just 0.2 ppm SO3 and extremely small amounts of sulfuric acid. So that's what we have in our vent gas that's going to the scrubber. And this scrubber is a little bit interesting because we're adding some hydrogen peroxide to the quench loop. And what the hydrogen peroxide does is it oxidizes the SO2 back into SO3. And when it becomes SO3 and there's all of this water in circulation, then that water will convert the SO3 to sulfuric acid, which will stay in the liquid phase, meaning we have a very clean vent gas that's now at 0.01% SO2. And we have a little bit of we have a water drain. It's got a very small amount of sulfuric acid in it still, but not very much. So that is how this process removes its SO2 as opposed to the other one that uses a caustic scrubber. But this one requires the addition of some hydrogen peroxide to do that. Okay, let's see. I've got a couple of questions. Okay, which thermal property is used for the thermo column for the first column? Now, when you say first column, that would be condenser and quench and scrubber. Both of these are going to use. Let's see. I believe this one is using the NRTL package with the Laliberte. No, this one's back to using Ping Robinson. There's not enough sulfuric acid present to necessitate using that NRTL. So it's only in this flow sheet in the wet column where the condenser and the quench are using the NRTL modified NRTL thermo package, only in the condenser and the quench. So in this flow sheet, the combustion, the converters, and the scrubber are all simulated using Ping Robinson, and it's only this condenser and quench flow sheet that needs the modified NRTL. Okay, so the sulfuric acid rich column in the previous example, if it's sulfuric acid rich column, it's going to be the NRTL with the Laliberte option. Okay, yeah. All right, so this is the rundown of the wet sulfuric acid process. Do I have any questions about that? Okay, so now I'm going to go. I've showed you most of the things that I'll talk about in the next example, but these are 3 different exercises I'm going to go through step by step to show you how to build the things that I find to be relevant or are kind of unique for sulfuric acid production simulation. A lot of stuff is not very unusual. You see it in other processes, but these are the 3 things that to me seem a little bit different and worth noting. So the first thing we're going to do is we're going to simulate a burner, and I've got a solved case right here that you can refer to, and I'm going to send these. Yeah, let's step back a minute. I'm going to place this video that we're watching on YouTube, so you'll be able to see the video, and along with that YouTube video, there's going to be a link where you can go and download these 3 files: the dry sulfuric acid process, the wet sulfuric acid process, and then these exercises. So this exercise file with the unsolved sections on it is something you're going to be able to obtain, and you could open this and you could go through these very same exercises. On top of that, there are instructions provided for the exercises. So over here we have the flow sheet itself, where we're going to make modifications and we're going to perform the simulation, but we're going to use the instructions I've written over here. So in this sheet called Instructions 1. I've got all of the instructions needed to perform the combustion flow sheet exercise. And then I've got the converter flow sheet exercise, all the instructions for that. And then on Instructions 2, we go through how to create a reaction set, because we need that reaction set in all of those reactive distillation columns that do SO3 absorption. So that reaction set needs to be defined. And then also the NRTL environment. Here's a step-by-step walkthrough of how to configure that environment if you ever need to do that. And then the last one will be how to simulate the absorbers using this reaction set and this special modified NRTL environment. Okay, so let's go to the combustor. I won't be going back. I printed out the instructions, so this time I'm not going to have to go back and forth. So I'm just going to read from the instructions and perform the steps on this flow sheet. So we're going to start on the combustion flow sheet. There is a solved case that we could use for reference. There is this property stencil shape that I'll show you real quick how to find that. There's a set of there's a stencil that's not always checked on. It's never checked on a new project when you open it, but you have to check more shapes and check this to access this property stencil list. But in here, there is a shape called copy stream conditions. There, right there. This shape, you can drag it onto the flow sheet, connect it. The upper stream, line has to connect to the stream with the source information, and then this lower connection line goes to the stream where you'd like to transfer all of that information. So this unsolved feed stream is an exact copy of this solved feed stream, and I can make any changes to the mix of sulfurous feedstocks or the air rate or the fuel gas. I can make well, no, actually only to the sulfurous feedstocks. I can change these. They'll affect the solved feed, and those conditions are transferred to this unsolved feed stream. So, you could use this tool to test other hypothetical blends of sulfurous feedstocks, and it will solve the air rate so that you get a targeted excess oxygen, and it'll solve the fuel gas rate so that you get a targeted outlet temperature. So that's what this simulation is doing, and we're going to replicate that. We're going to configure the burner and the heat exchanger and the solvers for the air and the fuel gas so that we achieve our desired outlet oxygen content and outlet temperature right here. Okay. So in the burner block, we're going to open this, and what we need to do with the burner is set the type of reaction to Gibbs minimization. And after you set a reactor type to Gibbs minimization, then you're prompted to choose a Gibbs set. And we have a lot of these Gibbs sets that are predefined sets of components to use and constraints of different types. And they are almost all related to sulfur recovery units. And in this case, we have so much oxygen that all of the species that can oxidize are going to oxidize. We have, excess oxygen. So we're going to just choose this general Gibbs set, and we're going to let all of the components be allowed to participate in the Gibbs minimization reaction. So we're not going to uncheck any of these components to remove them from the reaction. And then all blocks need a pressure drop specification. So we're going to set the pressure drop to 0 psi. I don't think we set anything else here. So at this point, now we have specified everything that we can. This burner outlet stream is gone from red to maroon, so it means there's no more specifying possible. And I'm just going to execute the block. I'm not showing the message log right now, so I can't see what happens, but there is a we have solved it. It's gone to the green state, so we've solved this reaction. But we've got a very poor temperature, very poor oxygen content. We need a lot more oxygen. We need a lot more natural gas to bring the temperature up. So the first thing, well, the next thing I want to do is to specify the waste heat boiler. So inside the waste heat boiler, we only need to specify the pressure drop. And we want to have 0.5 psi pressure drop. And we're going to set the outlet temperature to be 760 degrees F. So now that solves. But we're very far from our desired conditions because we haven't got the right air rate or the right fuel gas rate. So the first thing I want to do is create a solver that okay, next thing the instructions asked to do is to add a combustion analysis to the unsolved feed to get an idea of how much oxygen is required to combust this stream. So in the unsolved feed stream here, we have the composition, and we see that there are a lot of species that could oxidize, but we don't know how much oxygen is really needed for that. And we have an analysis, an extra calculation we can add called the combustion analysis. If we add this combustion analysis, and then we press the solve button, we can see how much oxygen is required to combust the sulfurous feedstock stream. And here we need 6 moles per hour of oxygen. So I want to make an initial guess to bring this to complete combustion. So right now I have 5 moles an hour, but air is about 20% of the feed stream. So I multiply 6.1 from the combustion analysis times 5, and that's about 31 moles per hour. So let's change our initial guess to 31 moles per hour, and then re-execute this flow sheet. So now we're getting a little warmer. Okay, now we have at least a little bit of excess oxygen, and we have a temperature of 1451 degrees. So we're getting in the reasonable range for a burner now because we've supplied enough air to completely combust the stream. But we want to do better than that. We would like to make a solver so that we can exactly get 3 mole% oxygen in the outlet. So to do that, I double click on the stream for the air rate, and there's the property, the molar flow of air. So I want the molar flow of air that gives exactly 3 mole% outlet oxygen. So I'm going to add a solver. We're going to create simple solver. I'm going to always give it a name, so it'll be, I put the unsolved because it's for the unsolved case to distinguish it from this other solver that was built for the solved case. So here is our solver. Now we need to add the measured variable. We're going to adjust the air rate. You can see here the calculated variable is the ProMax project flow sheets combustion stream unsolved air molar flow. That's what is going to be adjusted but we need to adjust it so that the burner outlet stream has 3 mole% oxygen. So we're going to add a measured variable. I'm going to go to the flow sheet called combustion. And the process stream is going to be the burner out stream. See, now I forgot something. Okay, yeah, that was the burner out stream. I'm sorry. Got to go back through here and find that exact property. So the stream is called burner out. It's going to be a total phase composition. It's the oxygen on a mole fraction basis. So you select mole fraction and then you choose oxygen. And it's in percent right now. It could be changed to some other units, but percent is good. I'm going to provide a name here for this measured variable and then press add. So now you see in this list, here is the oxygen, mole% oxygen in the burner outlet stream. So it's an available measured variable, but now I've got to use it in a residual equation. So I need to write an equation that's going to equal 0 when we have arrived at the correct solution. So whenever the oxygen content is 3%, I've reached my target of 3%. So I could make an equation that is O2 minus 3. That equation, when this equation equals 0, we're at our solution. But this isn't really well scaled yet, so I'm going to make it better scaled by dividing the target value and then subtracting 1. So now this is a scaled residual equation that will drive the air flow rate to the correct flow that gives us an oxygen content of 3%. And in this case, I also want this solver to perform at a faster than the solver for the natural gas that I'm going to add. So I want to add a higher priority than the default, and I'll let the other solver be at its default. So let's see if we can converge this solver. So you see it's adjusting the air rate, and it takes 2 small steps, finds out what the derivative is, and then takes a shooting step towards what it thinks will be the right answer. Okay, so now the air rate has been adjusted so that we have 3 mole% oxygen at the outlet. What we don't have right now is we don't have enough fuel gas to provide a temperature of 1950 degrees. So we need to add some fuel gas. But as we add fuel gas, we're going to also need extra oxygen to combust that fuel gas. So if we find the fuel gas that brings us to 1950 degrees, we're also going to need for the airflow rate solver to adjust so that it gets to the 3% oxygen level also. So these 2 solvers are going to be running simultaneously, but I want the air flow rate solver to always be the faster or the inner loop solver, and then the natural gas flow rate solver is going to be on the outer loop. It'll run slower. So we're going to go through the same process here. The property of interest is the temperature of burner out, and because it's a temperature or one of the scalar quantities, I can do an easier method for getting that property in my solver. I just have to go to the property, which is the temperature, and I right click and I copy the moniker of this property to my clipboard. And now I can go to the fuel gas stream. I'm going to create a simple solver again. going to be unsolved fuel gas rate. And now instead of navigating through the object tree of the whole simulation project, I am going to choose whatever is sitting in the clipboard with this radio button here and give it a name. I'm sorry, that's temperature. Just T. And I'm also going to create a residual equation. So it's the temperature divided by the target temperature, and then subtract 1. Now this will take a little while to converge because these two loops, they're far away from the right answer. So it takes a while to get close. Once you get close, each new test of this isn't so time consuming, but on this first one, it does take a little while. Any questions about this? Okay, I have a question, how to assign priority to a calculation. And I think the question is, how do you decide which is the faster one and which is the slower one? And that is that's kind of a trial. Sometimes there's some intuition that helps you know which one is better to use as the inner loop. Even this one with the air rate as the inner loop, it's still a pretty slow solver. Most solver systems that I do don't take so many iterations. Finally, we got to the solution. But here I've got, there's a, one thing you can do is you can open the project viewer and you go to the bottom where there is this solver summary. And in this, we have all of the solvers in the ProMax project. So right here, we have an air rate. We have the unsolved air rate and the unsolved fuel gas rate solver. And you can set their priorities right here. Now, the larger the number for the priority, the more of an inner loop solver that is going to be. So in this case, the priority is 10 for the air rate, which means it is larger than 0. So this is going to be the inner loop, and the unsolved gas rate has a lower priority, so it's going to be the outer loop. And you can have several nestings of loops, and they're, how inner or outer those loops are is determined by their priority number. You can have several solvers at the same priority number, or you can have them different. They don't have to be contiguous. You don't have to say 0, 1, 2, 3. You can go 0, 10, 100, 1,000, whatever it is, as long as they're greater than 0, and you can tell which number is higher than the other. Recycle blocks also have priorities, and we haven't seen any of those right now, but recycle blocks have priorities, and usually I put all the recycle blocks at the same priorities. So I'll pick a priority number like 5, and all the recycle blocks will share that same priority level. But solvers usually work better when they're at different priority numbers. So I hope that answers your question. All right. Now let's go to the exercise for the converters. Here we have, I'm going to solve this flow sheet so we can, here you can see that the first reactor bed and heat exchanger afterwards, they are already configured for you. So you could use these as examples to see how to configure the rest of them. And here we have this set of beds on the left-hand side, which is for the wet sulfuric acid process. So it takes the SO2 rich gas in its wet form from the combustion simulation upstream. It takes that gas and doesn't even cool it. It just goes straight from that previous waste heat boiler straight into the converters and does the simultaneous SO2 oxidation and SO3 hydrolysis. So you can see in this block, we have the Gibbs minimization is chosen. The components are oxygen, water, SO2, SO3, and H2SO4. So both reactions are being considered in the wet process. Over here on the dry process, we're just doing a quick and dirty estimation of the feed stream to the dry process by removing all the SO3 and sulfuric acid and water using a divider block. So all the water, let's see, maybe not all the water, but we look and see how it's configured. We have 99.5% of the water is being removed, or 0.5% of it is being sent to stream 2. So we have all the SO3 and H2SO4 are removed, and then only 0.5% of the water is being allowed to proceed to the catalytic beds. We heat it to 850 degrees F, and then inside of here we have the Gibbs minimization again. You go to the components tab and you see that only oxygen, SO2, and SO3 are allowed to react. So this is a different type of catalyst, I guess, and it is designed to not have any water present. I really have no idea what the differences might be between a wet and a dry catalyst, and I have no idea what the pros and cons are between the two. So I just have learned what I have to do in ProMax to simulate it and match a set of plant data. But beyond that, I'm really not the right person to ask about. Somebody in here might be able to answer that, but I don't know. All right, so our job here is to simulate the second two beds and the wet cooler, which is a reactive heat exchanger for the wet system, and also the inner stage coolers we're going to simulate. They're just simple heat exchangers. And on the dry system, we have 3 beds and 3 coolers to simulate. So I have instructions that are on that page, instruction 1. I'm just going to go through here, and it's going to take a little bit of time. There's going to be a lot of clicking and adding numbers, but just watch, and I'm not going to say very much. I'm just going to do it, and there will be you'll be able to watch the video and read the instructions and do this yourself later on if you want to do that. So let's see, the first thing is all the heat exchangers and reactors are going to have 0.08 psi for the pressure drop, and all the reactors are going to have Gibbs set minimization. Gibbs type, Gibbs minimization, Gibbs set is general, and for the wet reactors, we're going to have oxygen, water, SO2, SO3, and H2SO4 participating. In the dry reactors, it'll only be oxygen, SO2, and SO3. And all the reactors have the bypass fraction at 2%, and the maximum phases equals 2%. So let's configure this first reactor. First, we need the Gibbs set type to be, or the reactor type to be Gibbs minimization. The Gibbs set is general, and the components are going to be oxygen, water, SO2, SO3, H2SO4. We're going to have 0.08 psi. We're going to have bypass fraction of 2 phases, and that should be all we need to do. Okay, there, that one's solved. And in the heat exchanger, we're going have 0.08 psi for the pressure drop. And we are, in the instructions, it tells us we're going to have an outlet temperature of 707 degrees F. Do the same thing in this reactor bed. All right, and then we're going to have the cooler, and it is reactive. So this is a reactive heat exchanger. Use Gibbs minimization again. General 0.08. That might have had a different pressure drop. I can't remember. This one is actually going to have a bypass fraction of 0% and 2 for the maximum phases. And the outlet temperature for this one is 585 degrees. So now we have the wet sulfuric acid set of beds and wet cooler is simulated. You can see here there's this, whoops, there is a property table set up to show you the streams, the relevant streams. So we have 0.3% SO3 on the inlet, and then going to the condenser, we have something's not working right here, I don't think. We still have a lot of SO2. I didn't convert everything very well. Feel like I'm missing something. It's like I don't have enough oxygen. %. 95% conversion of the oxygen, 40% conversion of the SO2. Yeah, somehow I need more oxygen on the inlet. I can't believe that I messed up like that on making this exercise. But I don't seem to have enough oxygen to convert all of the SO3 to SO2 to SO3. Yeah, I need extra oxygen. Maybe I could get out of this mess by doubling the oxygen content here. I'm winging it right now. I made a mistake, didn't check something when I built this. I'm gonna add more oxygen, solve this. So that's gonna take a minute or so. You know, I did a webinar on alkylation a few weeks ago, and there was an exercise that I couldn't do during the class, and I seem to be cursed this way. When I make these exercises, the first time I feel like I do them right, and then I go to the live webinar and something goes wrong. Let's see if that is enough oxygen. We're still depleted. We still have all of our oxygen gone. This is oh, I know what happened there. I'm still transferring from this other one. All right, that's a lot better. That's what I was hoping to see. Here we have the we have a lot of SO2 on the inlet, very little SO3, and now we have no SO2 in the outlet, and we have a lot of SO3 and a lot more sulfuric acid. All right, so that I'll fix that so that hopefully it's good enough now, but I'll correct the file and the instructions for y'all to use later, so you shouldn't have that problem. And let's see if we can go unscathed through the next set of reactor beds where only the SO2 oxidation is going to occur. Let's start doing these. Gives minimization, 108 psi, and I need to limit the components. And here we're only going to have oxygen, SO2, and SO3. We're not going to check water and sulfuric acid. So that converts. And let's go to let's do all the beds first. And we have outlet temperatures to choose. We want to have 840 and 860 for the 840 for the cooler outlets. And for the dry cooler, we want 335 degree outlet temperature. And let's see if this. Okay, so we have conversion. We started out with no SO3 going in, a lot of SO2. Now we have much less SO2 going out and a lot of SO3 going in. we have any oxygen left. And we still have oxygen here, so I think this is the performance you would expect out of this set of beds. So you're going to have that amount of SO2 in the outlet. You have much less SO2 in the outlet of the dry system. So that's one of the differences there. All right, any questions on that? That was fun, wasn't it? Okay, the absorbers, we're going to have one of the absorbers from the wet system, the wet sulfuric acid system, which is going to be the condenser column that we showed in the example for the wet system. So we're going to simulate this one, and then we're going to simulate the absorber where we dried, where we had the wet SO2 gas, and we dried it by passing 98% sulfuric acid over it. So we're going to simulate these two absorbers in this case. We have the salt, because it's taking up a little bit more space, it'll be hard to put the solved case and the unsolved on the same flow sheet. So here we have the solved case is on one flow sheet, and I've got an unsolved case that's pre-built. The structure is built, but the environment is not selected. That environment with the NRTL is not selected, and it doesn't have the reaction for the SO3 absorption added to it. So we've got to create that reaction. We've got to create that special property package, and then we're going to specify the blocks here so that we get proper SO3 absorption in these distillation columns. So there'll be reactive distillation columns when we're done. So the first part of this is we're gonna work with reaction sets, and this is sort of a global exercise. It's not particular to this single flow sheet. So we're going to create a reaction set that could be used by any of the flow sheets, and they're going to exist in this category we have in the project viewer that's called reaction sets. So you see here we have all of our flow sheets. I'll collapse these. We have all of our flow sheets, a collection of these, and then there is this category down here called reaction sets. I've already created the reaction set for the solved case. So we can double click in here and we can see that it has this reaction included within the reaction set. So a reaction set can contain several different reactions. So there's a lot of times there's parallel or series reactions, and you want several reactions to exist in a reaction set that one reactor will run or use, a distillation column or reactor. But in this one, we're going to make a reaction set that only contains this single reaction. And this is a conversion type reaction set. So we're going to make the reaction set and declare it to be a conversion reactor. And then we're going to add the particular reaction to it. And if we want to see we can open this reaction to see the more properties of it. So you see the stoichiometry is defined here on the left-hand side, and on the right-hand side, we say that this reaction only participates in the liquid phase, and the conversion base is SO3, and we have a default conversion factor of 1. So when this reacts, all of the SO3 will convert to form sulfuric acid. That's this reaction that sits inside of this reaction set. So we're going to basically replicate this entire reaction set, except it'll be just called SO3 absorption. So what we do, and these are steps that are in the instructions provided, we're going to right click on this thing called reaction sets. We're going to right click and we're going to add a reaction set that's called SO3 absorption. we're going to set it to be conversion. And when you check conversion, you have to go over here and uncheck kinetic. It's a little confusing right there. And we need to add a new reaction. It'll be the only one. We're going to call this and we're going to start adding components. So this reaction, it uses SO3. It uses oxygen. Actually, that's wrong. It uses water. And forms SO4. And in the stoichiometry, we consume an SO3, we consume a water, and we form an H2SO4. And the reaction is only in these distillation columns. If you're going to use a reaction in a distillation column, you have to choose either the liquid or the vapor or the heavy liquid phase, maybe, if it exists. But you can't use the total phase for a reaction in a reactive distillation column. Conversion base will be SO3, and it asks us to use 1 for the conversion base here. I think that's all we have to do to create this reaction set. And now I want to check the active box to make it an active reaction set. Okay, so the reaction has been added. So now when we create our environment, adding a reaction set is one of the steps you do in configuring an environment. So we're going to create that environment right now. So right now this flow sheet has been, when we made the flow sheet, we gave it the environment of the combustors and the combustion and converters, because that's really the only environment we have at this step. So we're going to use that as our basis. The component list is all the same. And we're going to duplicate that one that is using Ping Robinson right now. We're going to go to active environment, edit environments, and we're going to choose our combustors environment and then duplicate it. The main thing about duplicating is it copies the component list. That's a lot of work to recreate and match up a component list. So duplicating an environment is a really nice thing to be able to do. We're going to name it liquid acid. The components are the correct list of components. But we go to property package and we're going to choose NRTL as our base property package. NRTL Ping Robinson. And then after that, we're going to check. So it's got all the parameters for NRTL Ping Robinson in its environment, but we're going to customize it by choosing use custom package. So now we're going to deviate from the NRTL Ping Robinson in a couple of little areas. We're going to choose a property called molar enthalpy. This is really stuff I feel sorry that we're in a state still where you have to do this, because I don't like for people to have to go into this area very often. I don't like it when I have to go into this area. It's a strange, uncomfortable area for me. It's very deep into the internals of ProMax. So we did that with molar enthalpy and we applied it. Now we're going to do the same thing with molar volume. And we're going to scroll down to the very bottom and choose the Laliberte Cooper class for light liquid and heavy liquid mixtures. We're going to press apply again. So now the thermo calculations are going to use NRTL Ping Robinson, except for molar volume and molar enthalpy, where it's going to apply that special Laliberte Cooper class method. That's the only difference it's going to have from regular NRTL Ping Robinson. But we're going to leave it like this. And now the other thing we have to do in the environment is in the reaction sets, we have to look at our available reaction sets and select whichever ones we would like to be selected or available for flow sheets that use this environment. So we want this SO3 absorption reaction set to be included in this environment so that any flow sheet that uses this environment will have that reaction available to it. So now we've configured this liquid acid environment. The next thing we need to do is associate this flow sheet, the absorber's unsolved flow sheet, has to now be associated with that new environment we created. So in here, you go to ProMax, active flow sheet, and you switch from the assigned environment being combustion and converters to liquid acid. Press OK. So now anything that's happening on this flow sheet is going to use the component list, the thermo package, and the reaction set that's been configured in that liquid acid environment. So this is now able to do reactive distillation and the proper thermodynamics to separate to treat the rich sulfuric acid streams properly. We can solve this, and our feedstock feed streams are now green. So they're solved. So all we have to do now is configure the condenser and the absorber. So let me do that real quickly, and then we will finish this webinar. It's the last thing we have to do. Okay. We're gonna, for both of these columns, there's a convergence tab in these columns. They default to Boston Brit with a K damping of 0. Most of the time, I have really good luck by switching to composition dependent and K damping of 4. That is Barry's default. So other people may have their own, but I'm gonna stick with what works for me. Many years ago when I started here, the Boston Brit was more effective at most columns, but they've been making changes to how the column algorithms work, and it seems like composition dependent works a lot better more often now. In both of these columns, we want to select in the process data tab, we want to go to user reactions and choose our SO3 absorption reaction. And we have to check the stages that we want these to happen on. So we check both stages. And in the reaction set tab, if you want to change your conversion to some other number, conversion factor per stage, you can do that here. But we're going to leave in the condenser, we're going to say that all SO3 and water react to form sulfuric acid. And in the absorber, it's going to be a conversion factor of 0.94 instead. I think we can solve the absorber right now. No, I didn't put a pressure drop in there yet. Never mind. Okay, the condenser pressure drop is 0.3 psi. So it's in the stages. You go to process data, stages, and then you can set the pressure change to 0.3 psi. And then in the absorber, you go to stages and set the pressure drop to 0.5 psi. And now I believe the absorber will solve. That one did not solve. And what I think works best in this case is to go to the reactions and uncheck the reactions first.
I believe you also have checked the Boston Sullivan KB, but okay, this.
So I could solve it without the reactions on. And then now that the column has a good starting case behind it, it is now able to solve. So it was just too big of a jump to ask it to solve both distillation and reactions without having any set of initial conditions behind, in the back of the columns database. But if you have if you have a pre-solved case that's solving the distillation, and then you add the reaction on top of that, it's much easier for it to solve. So that's what we have to do in that case. Now you can make pretty much any change and it'll solve. From my experience, it's very robust after it gets that first solved case behind it. And now with the condenser, we have an overhead condenser, and we want to set the overhead temperature to be 212 degrees Fahrenheit. So we go inside of the condenser and we go to specifications and we add a column specification called phase property. The temperature is a property of a phase, of a stage, of a column. Let's go top temperature. All three phases have the same temperature, so it doesn't matter. Temperature, set to 212. Check that it is a specification. And let's see if we can execute this column. Solved a lot easier yesterday. Let's see, did I specification on this stage 1 total phase temperature? Maybe I have maybe the specification is on the wrong stage. I think it should have been the other way, but let's see how I did it in the solve case, because I really can't remember right now. Condenser total temperature. Okay. So the way I had it the first time is what we need. That makes more sense. And execute this. Do I need to uncheck that box? That is unchecked. Okay. Okay, I finally got it. All right, so now we have both of those solved, and everything looks good. So with that, do you have any questions about the absorbers or anything else that we talked about in the entire webinar? Because we ran over time a little bit, and that is all I have to present. So thank you very much for listening, and I hope you got something out of it. If you have any questions, please contact me later, and I will send you notification about getting where you can find all this information on YouTube and our download files.